Hi, I'm Rob Stupnowski, a senior lecturer and remote pilot at the University of Texas at Austin's School of Architecture, and this is a Point Cloud Pedagogy. A Point Cloud Pedagogy is the exploration of providing students with new insight into historic preservation using point cloud technology as a vehicle. How do you document a historic site, an object, a building, interiors, topography, or machines for that matter, at a high level of accuracy, giving us a permanent snapshot in time? Photogrammetry and 3D laser scanning methods of documentation are not necessarily new. Improvements in technology has made this far more accessible to students. How to grasp, process, and draw conclusions using photogrammetry and 3D laser scanning tools by the students will allow them to discover what it takes to document a historic site. They will also learn how to make key decisions within the workflow to ensure they're capturing the full story of that site. The story of a historic site can best be told at varying scales and levels of detail within Point Cloud itself. This offers the opportunity to analyze each part of the site and visualize the 3D model through Point Cloud, wireframe, shaded and rendered views. 3D laser scans and photogrammetry allow the user to develop a freestanding model of underground interior spaces which would otherwise not be seen. This can provide a whole new insight on a historic site, provide clues as to what might be missing and what might need to be further investigated. In the last decade, point cloud datasets created using various technologies have revolutionized the way we document in 3 dimensions. An added benefit of this process happens to be a byproduct of the technology itself, extraordinary images that would have previously been impossible to create. Understanding the blend of sciences, art, and precision of measurement provides new perspectives, forcing us to wonder what we're viewing. What is the story behind this image? How would the student approach this?
Students learned what it took to implement the photogrammetry and 3D laser scanning forms of documentation for a given historic site. Using the tools on hand, key decisions are made along the way to ensure the full story of that site is captured. Focus on material, texture, both interior and exterior space are considered as each scan location is chosen and UAV flights are implemented. If more detail was needed, additional scans are performed for better coverage or UAV flights are added at different altitudes, thus increasing the overall detail of the final densified point cloud. Next, we explored 2 historic sites. First up is the Wildflower Center. The Lady Bird Johnson Wildflower Center at the University of Texas at Austin is the state botanical garden and arboretum of Texas. Wildflower Center is one of the more complex sites as it consists of multiple buildings and expansive landscape. The goal and focus for this site was the interior and exterior of the Wildflower Center Central Tower. This tower is made of organic stone and brickwork and poses a high challenge in assessing how to capture this. Scanning methods are 3D laser scanning, aerial, and terrestrial photogrammetry. You can see images of the tower here that the pathway is tight. The students would have to figure out how to place the scanner and have good line of sight, good coverage, and be able to capture the detail of the texture throughout the tower itself. You see here the chamber is also tight and void of light. Of course, the 3D scanner doesn't really need light, but is the perfect tool for scanning something this small. Dual flight path provides the best overlap for capturing more surfaces of each building and the tower itself. The detail of the stone is revealed with multiple altitudes as the UAV flies over in a double grid format. You see here, this dual flight path of grid and orbit provide enough waypoints and coverage, which provides ample detail in the point cloud itself. The students learn to make decisions building a thorough ground control point layout to ensure the stone tower is well within the triangulation of the UAV flights and 3D laser scans. Each control point resides on a different level, providing a higher level of accuracy for the densified point cloud. Color, texture, and proximity to the tower are considered as the ground control points are laid down. Only a few tie points are needed at a distance from the tower to provide an additional accuracy check. Discovery of the overall size of the tower is achieved through measurement within the point cloud itself. In this animation, we visualize the progressive stages of the point cloud from a rough draft with only the automatic tie points calculated, then to the densified higher resolution point cloud, and finally to the high resolution 3D textured mesh, which reveals the detail and color of the stone tower. Using only the densified point cloud, the students learn to build vignette models to achieve views and vantage points of the stone tower which would otherwise not be possible on the site itself. Using a 3D clipping box and a 3D section cut, we are able to explore those views. Visualizing the 3D laser scan point cloud, we begin to investigate the material, texture, and spaces of the tower, and also prove the 3D laser scanner location layout worked. In this view, the small spheres represent the 3D laser scanner locations as a procession climbing the tower's winding staircase. Next, we begin to deconstruct the stone tower by visualizing the interior scans as a freestanding model. In this view of the tower, we discover the interior staircase, brick walls, and internal upper chamber without the thick stone skin revealing its own textural personality. Further deconstructing the internal freestanding model, we can now investigate the large stone wall texture and staircase. The arched stone ceiling is especially interesting as we can now see it on its own. The gray tone point cloud reveals the depth of texture and gradation of the curves in each wall. The upper internal chamber can be investigated and measured as if it were a freestanding structure. This provided the students with great insight into how this stone tower is made. Rendering the freestanding model as 3D vignettes in plan and elevational views, we gain a further understanding of the change in material and depth of the brick and stone textures. The stepped brick in the oculus is very apparent, and the brick course change in the main upper chamber shows as a reveal. In this view, we investigate the center oculus using a gradated collage of the densified 3D point cloud produced from photogrammetry, 3D laser scans, and still images of the dome itself. This is a result of processing an accurate point cloud and proven with overlaying each method of capture with the actual image at the end to compare. Deconstructing the point cloud into drawings enabled the students to further investigate the Wildflower Center stone tower. In this view, we pull the tower apart, visualizing possible levels and plan while revealing the internal chamber and stair. There is now insight on where the internal chamber resides in relation to the outer stone wall. The discovery here is the chamber, stair, and outer wall are not symmetrical within each other. The section drawings tell a revealing story. Here we overlay the internal chamber 3D laser scans, revealing where the interior resides within the overall tower. Color mapped to the point cloud allow us to better see the gradation and curves of the chamber and stair tunnel. This set of three drawings is a composition of the densified point cloud generated from both photogrammetry and 3D laser scans, along with the building context. Further refining the densified point cloud into a schematic drawing set reveals the detail and accuracy of measurement. Views consisting of axonometric section, north, south, east and west elevations, and three plan drawings to round out the schematic set. With this, measurements are made to discover the height of the mid-level and overall height of the stone tower. And taking one more step, We investigate further into the point cloud by using only a section line drawing. That line drawing is seen here as a populated drawing with rendered backgrounds. The students approached this site with an investigative eye. There was a story to be told using a combination of 3D laser scanning and photogrammetry. How to set up a procession of scans to ensure the highest level of detail and texture were seen, and flying the site from above to capture the overall picture provides a great insight into what this Wildflower Center tower is all about. Our next stop is the Seaholm Intake Building in Austin, Texas. Densified point clouds were produced using a combination of 3D laser scans, aerial, and terrestrial photogrammetry for the Seaholm Intake Building over the course of a week. Hundreds of images were taken to provide adequate overlap of the interior photogrammetry. Key decisions were made along the way to ensure that interior concrete texture and surfaces were captured. Several loops and camera angles are seen here as we inspect each tie point for good, accurate coverage. The resulting 3D mesh and textured mesh are accurate. Applying the color tone study to the model revealed the light sources throughout. Our result is a clean 3D textured mesh model to investigate. This textured mesh section breakaway, as a self-standing model, reveals the subterranean chambers which are otherwise not seen from the outside. At each section cut, there is an opportunity to investigate each floor, facade, fenestration, and concrete texture. The opening in the floor is clear in this view, as well as the slots in the perimeter floor, which are currently covered with plywood. Historically, each slot held a piece of machinery supporting the function of the building. The waterfront facade could only be captured by using a UAV. In this case, the UAV was flown manually along the front of the facade to capture as much detail as possible. A high level of image overlap was used to ensure the facade's concrete reveals would exist in the point cloud model. In this view, the interior was captured using all three methods of acquisition. The challenges here are to find a way to document the hidden concrete ledges which are out of reach both from the camera and 3D scanner. Precise flight of the UAV was the choice to fill the voids of the interior surfaces, knowing there will be some aspects missed. Inspection of the image overlap provided good insight into ensuring an accurate point cloud of the space. Structure C of the Seaholm Intake Building provides its own set of digital documentation challenges where machinery obstructions exist throughout. Precise flight of the UAV was required to capture the upper concrete surfaces accurately. Several layers of loops around the space and multiple camera angles were used to capture the hidden surfaces throughout. This resulted in a great level of image tie point overlap, providing an accurate point cloud and clean 3D textured mesh. Exploring the 3D laser scan point cloud, we can clearly see the large subterranean lower chambers where the water was fed into the main Seaholm power plant building. The large circles on the lower chamber walls provide clues as to what may have been. The discovery here is the smaller structure C is not as deep as the other two main chambers. This is a rendered view of the scans, offering great detail and accuracy in the concrete's texture. This is a Point Cloud Pedagogy. I'm Rob Stepnowski. Thanks for watching.